Thanks for the introduction. Can you see my screen? Just want to make sure. Okay. Good afternoon. I'm Swamit from University of Wisconsin-Madison, and today I'll tell you how we can use low-cost lasers to flip bits in DRAM. And our broad goal here is to build an experimental methodology that can help us understand the vulnerabilities of current and future memory systems. So we are deploying billions of DRAM devices, and majority of those are vulnerable to row hammer attacks. I don't need to motivate this crowd why DRAM security is important, but it's really important that we understand why and how these vulnerabilities occur, and more we know about them, better we can defend against them. So that's why we are trying to build this experimental methodology. We know that these vulnerabilities result from aggressive technology scaling. So this is a nice picture that shows how capacitor and cell transistors are stacked on top of each other. And they are really crammed in a small space, and that results in the small feature size results in increased vulnerability. So characterizing and understanding row hammer and other vulnerabilities are really important, but we know that it's very challenging also, because to reproduce row hammer, we need to know the internal row level mapping, which is purposefully hidden. So we don't have a certainty on how rows are organized internally. And this information is essential to launch a row hammer attack. And in fact, one of the nice features of row hammer attack is you can use it to reverse engineer the internal mapping itself, but there are challenges, and one of the biggest challenges uncertainty is introduced by the out of order cores, operating systems, certain memory controller policies. And recently, there are defenses such as targeted row refresh that makes this characterization and reverse engineering challenging. And since we have all these tools, they are great. They give us a lot of information, but future designs can make this reverse engineering even harder. So that's why we need to think about how we can characterize row hammer, how we can reverse engineer internal mappings and understand it better. So today we can categorize these characterization strategy into broadly three categories. The first category is where we use software. You use timing side channels or performance counters to reverse engineer the internals, and then use that information to launch a row hammer attack and characterize it. Right, so this works really well, but sometimes it doesn't. So software-only strategies are very generic. You can launch them on many of the systems, but you have to also tune these attacks as per the system, and that takes time. That takes a lot of expertise. And there are several works that adopt this strategy, and they show how challenging it is, and they devise clever ways to launching row hammer. Beyond this type of strategy, there is this idea of using customized memory controllers where you can control the refresh rate, where you can disable the targeted row refresh, and sort of understand the substrate level vulnerability better. Right? So by reducing the refresh rate, we can improve the effectiveness of row hammer. Row hammer becomes more visible. We use it to reverse engineer the mapping and kind of go in this loop where we make row hammer attack better and better by understanding the internal mapping. The next thing that we can do is we can actually work with a system where we are working with a generic memory controller, something that comes into your x86 or ARM processor. But now we need a probing mechanism where we probe the refresh commands. And as soon as we detect a refresh command, we block it and sort of work with this setup so that we can, again, reverse engineer things effectively. So all of these tools are really interesting. They give us a lot of insight into row hammer. But one of the challenges with DRAM is its growing complexity, right? So one of the biggest challenge now is how do we do these characterization studies with stacked memories? For example, let's say if we want to probe a bus and sort of understand what's the frequency of refresh commands that is being sent, or use this type of probe and fault inject type of methodology, that's really not possible with stacked DRAM. So on Apple's A14 SoC, the DRAM die is inside your package. So there are no pins accessible where you can probe and understand more about the system. So we are motivated by some of these constraints, and our goal is to develop a precise fault injection strategy where we don't need pins to do fault injection. And a broader goal is to understand if there are new vulnerabilities inside these modern DRAM devices, enable fine-grained reverse engineering, and essentially a meta point here is to develop a reverse engineering strategy that can work with these indirections that are forced by the system designer, right? So the key insight of our paper is kind of old, right? We know that DRAM cells are extremely vulnerable to temperature changes. The factor that we add here is use lasers that can induce local hotspots, right? So these hotspots are localized to a particular physical location, a very small location, and we can induce bit flips in this specific physical location. And our hope is that by using this localized heating, we would be able to reverse engineer the internals better, and also explore some new type of vulnerabilities. So this work is majoritarily focusing on how to develop this methodology. I'll explain the setup that we have built, and I'll go over the evaluation that we conducted, and towards the end, I'll conclude with experimental challenges. So we use these really interesting engravers, which are equipped with low-cost diode lasers. The nice thing about these engravers is they are mounted on a CNC machine, which you can use to do a precise XY movements, right? These are really, I would say, I should say affordable lasers, right? You can buy this on Amazon for $300, $400. And when we started this project, we did not know what type of laser one should use. We did a lot of research on what type of wavelengths work, what type of power work. But it's one thing to go with the theory, and the other thing is with practice. It's kind of different. So the key insight is you can use these diode lasers. Even the 2-watt optical power is good enough to cause bit flips in DRAM. If you want to learn more, of course, ask more questions or reach out to me about how we selected the laser and so on, right? So here is a quick demo of what we did. So this is a Raspberry Pi 4 board, and this is the target DRAM that we want to sort of perturb. And here is how you can sort of laser it. And the laser is kind of very precise. You can draw certain geometries. So in this video, we are drawing a line, but of course you can use many different geometries that you want to use to perturb the bits. The other interesting thing about this whole ecosystem is there is a nice software that lets you draw what geometries you want to engrave on the DRAM chip. And it's fairly easy to automate the setup so that you can experiment with different geometries. So the idea here is to use this laser and check where all we are getting errors, right? To flip bits in a particular physical location, and that gives you sort of addresses which are affected by the laser. And to do that, what we do is we write all zeros to all the memory cells, then we laser part of the chip, read and check the data, we store the errors that we have gotten and the addresses, right? So it kind of gives us a neighborhood information. That's something that we can use to reverse engineer the internals. So we use a 5-watt optical power. The laser is a blue laser. It's a 450 nanometer wavelength. Again, wavelength matters a lot. And we can control the duty cycle of this laser, engraving speed, and geometries that we can insert. So we have tested this platform with about 30 chips from 4 different vendors and across 3 DDR generations, and we have seen that we can flip bits consistently across all these chips. So let me tell you a little bit more on how we evaluated our setup. So one of the most important things about this setup is repeatability in the faults. We don't want random faults, right? We want our faults to be repeatable. So if we experiment with this laser once, we should get same set of errors the next time we experiment. So this repeatability helps us a lot when we are reverse engineering the internals. So we do this experiment where we sort of draw one line and we repeat this drawing for multiple times, right? And what we count is the unique errors or unique erroneous addresses we get with each experiment. So for with the first experiment, every error that you get is a unique address, right? With the second experiment, if you get the same set of errors, then the number of unique addresses would be 0. In this case, it's not 0, it's somewhere around 30. So in the first experiment, we got 100 errors. In the next experiment, we got, say 90 errors, but 30 of those errors were new errors. And if we go repeat this experiment multiple times, we see that after a 5th run, we don't see any unique addresses. So there is a good amount of repeatability in all these experiments. And the reason that we see some unique addresses even in the 3rd run or the 2nd run is because sometimes the laser movements are not very precise. So the engraver is also has its own set of limitations. But if you use a sophisticated laser, I think you can reduce these unique addresses. But overall, we see a lot of repeatability in these faults. The second thing that we want in our setup is the specificity of induced faults. And to test that, we did this really interesting experiment. We drew a solid line first on the chip, and then we drew a dashed line. And both the lines have identical locations and the length, right? So as you can expect that since the dashed line it has like a less power incident on the chip, it will have less amount of errors. So solid line had like 400 errors, the dashed line had about 50 errors, right? But what's interesting is if you compute the overlap or the intersection of solid and dashed line, all the errors that we got for the dashed line were present in the solid line. And if we draw a Venn diagram of these two sets, the dashed line is sort of completely inside this solid line set, right? It's a subset of the solid line set. So this was important to study because one of the things that we thought is maybe heat diffuses, right? When you are drawing the dashed line, there are gaps between two dashes, and if heat diffuses quickly, then we should have seen similar number of errors or some errors that are present in the solid line but not present in the dashed line, right? So this was something that we tested with this type of experiment. And the other thing that we saw is the dependence of data dependence of fault injection. And we see that we can induce both 0 to 1 flips and 1 to 0 flips. So overall, this characterization gave us the confidence of, we can induce bit flips in all DRAMs. These bit flips are precise. They are repeatable. And I think that's something that we wanted to test first before we move to the reverse engineering. But there are some challenges also. So one of the challenges, number of faults and power relationship is kind of nonlinear and chip dependent. So you need to tune the laser power based on the chip that you have. So there is one chip where the number of errors increase significantly after a 55% power, right? So x-axis here is the laser power that you're using, y-axis is number of errors that you see in one experiment. So we see this consistent pattern on the chip one that below 55, there are very few errors, and above 55, suddenly the number of errors increase. And this increase is kind of exponential. If you go to 60 or 70% power, we will have errors that we cannot even log. Whereas certain chips are significantly better, where we see kind of a linear or polynomial increase in number of errors. The other issue is faults are location dependent, which is both good and bad, because now we can actually focus on a particular location on chip and try to understand what's beneath that part. So if, for example, location 2 in all these chips have certain maybe have a highly sensitive circuitry that we are hitting, but it's really hard to know at this stage. So when we are designing experiments, it's also important to figure out what are the right locations to use the laser on. And lastly, the other challenge with these experiments is there is a visible package wear out, right? So this is a picture of a chip where we did a lot of experiments, and after you do a lot of experiments, there are these white marks that appear, and that's probably because we are burning the epoxy. But throughout our experiments, we have never seen a permanent fault. Even we subjected these chips to a really harsh conditions. So that's a testament to package guys, I guess. Even you laser it so often, you don't see any permanent faults. But definitely there are these wear out signs. But I feel we can solve this problem. There are standard tricks in laser cutting and engraving that people use to reduce this type of burning effects. Okay, so this was a kind of description of what we did. We would love to hear feedback from all of you. I'll conclude that we really need to develop new type of tools so that we can understand and study memory vulnerabilities better, because current strategies may or may not work in future. And that's why we kind of started working on this, and we presented this framework where we have tested 30 chips, and we see a repeatable and precise fault injection that we can do with this really affordable diode lasers. So with this, I'll conclude my talk and happy to continue the discussion.
Right. Thanks a lot for your talk, Swamit. Are there any questions from the audience? So you can raise your hands, you can type it in however you like, and then you get to ask the question. But maybe I first ask the question, give some time for the audience to ask their question. So my question would be, so what would be the precision of the faults and the location of the laser that you could actually sort of like trigger this fault on? So say, I trigger a fault on a certain DRAM row. Can I then, move the laser a little bit to trigger a fault on the next row or not? So say I want to reverse engineer the row ordering, for example.
Right. So I don't think we can be that precise, because one of the things that stopped us is the CNC mechanism that we have, right? So our laser head moves a little bit. Mm-hmm. So 2 runs may not be super precise. So the type of precision that you need there is micrometers, and I believe what we have is maybe hundreds of micrometers. Mm-hmm. Right? So that's one thing. The other interesting thing is, even on the DRAM chips, there are multiple dies, right? So how rows are really mapped across dies, that also plays a role. Maybe half of the row is on top die, half of the row is on the bottom die. We don't know that. So that's another thing that we want to figure out. Can we induce bit flips across, let's say there are 2 dies, right, across die, because there is a shadow effect that goes on. In theory, the laser spot size is 0.8 micrometers. So it's a really small spot size. So you should able to target, like the blast radius is around 300 bits but that's in theory, right? Again, we have not really optically tuned the laser. Like you can always use lens and like tune it so that it's very precise. Right now, it's just, it came out of the box. We started using it.
Cool. I have more questions, but I see that Stefan has raised his hand. So maybe you go ahead and ask the questions.
Very nice work, Swamit. Two quick questions. One about the methodology, which is whether you were running the system while you were doing this, and if you were, how were you able to control that that DRAM was not, the values were not changed by the software system, the software running on the platform, maybe the firmware or the software? So that's one question. How do you make sure that the bit flips you see are due to the laser as opposed to the random things on the platform happening? And my second question is about your results, whether you've seen any of the bits flip in both directions. I'm not sure if you've tested that, maybe you haven't, which is fine. But if you have, I would be interested to see if you've seen that.
Okay. Sure. I can talk about the first question. So we use memtest where we are writing zeros or ones. So we have tested both 0 to 1 and 1 to 0. And then laser sort of starts working. And this memtest is not really running on a operating system. It's like, UEFI type of system where you have like a linear mapping, and there is no real operating system. Like the bloat of operating system is really tiny, right? So that's why we can say that this is because of laser flipping the bits. I think in one of the experiments, my students were able to change the language of memtest 86 by flipping certain bits in the where the software was mapped. So that kind of confirmed that we are really, flipping the bits because of laser. The second thing, we have tested both 0 to 1 and 1 to 0 type of bit flips. So memtest has this feature where we use sleep test. It just writes zeros and sleeps, does nothing. During the sleep period, we laser the chip. So you can write all zeros.
My question was whether you've seen the same bit flipping in both directions.
Oh, same bit flipping in both directions? No. We have not seen the same bit flip in the board.
You have, so you've tested for it and you have not seen that.
That's correct. Yes. But again, this was not a very rigorous testing, but we actually tried to see, was there any overlap, and there was none.
Yeah. Okay. So there were two more questions in the chat, and I would love to ask them, but they came a little bit late, and we are out of time for the slot for this talk. Maybe I will write them. So shall we go ahead and ask?
Yeah, let's just give you, Swamit, a couple of quick.
So maybe try to answer them quickly then, right? So the first one is, can we do the same with low power lasers, for example, a laser pointer?
Yeah, and I'm afraid not, because you need to incident some amount of power. So the laser pointer is not the right tool. Engraver is a good tool to use.
Okay. And then there is another question. I'm not sure whether I understand it correctly, but it says that if we destroy a part of the memory, when will it be restored again?
We are not destroying the memory. We are just causing some heating that accelerates the charge leakage, and that's why we see errors. So we are not really destroying the memory. We actually tested that very rigorously.
Okay.